The discovery of fire is one of the landmarks in the history of man, for it led to a series of developments all involving the use of fire as the primary source of energy. Today, a country's technical advance is gauged by the amount of energy it consumes. But fire is not the only source of energy. We also get energy from falling water. In these sources of power, one can perceive the sun's radiant energy transformed through a benign alchemy and stored in many forms. And the sun itself draws its power from the atom. Thus, all energy is essentially atomic. Today we know that the sun is a vast furnace in which atoms burn. The release and harnessing of energy from the atom on Earth is one of man's greatest achievements, and one which may have the most far-reaching effect in molding the future of mankind. The primary source of atomic energy is the fission or splitting of the uranium atom. This is achieved in a reactor, which is essentially an atomic furnace.
Attention, the reactor is now critical. Attention, the reactor is now critical.
The development of atomic energy has assumed urgency because man has been using up conventional sources of fuel at an alarming rate, and these sources are not unlimited. They would last us barely a few decades. What then? The world has to prepare itself to do without coal, oil and gas, and to draw its power more and more from the very roots of matter. The world's atomic fuel resources are many times greater than the entire resources of coal, oil and gas. The search for fissile materials in India under the guidance of the Atomic Energy Commission has revealed rich deposits of these materials. Large deposits of atomic minerals have been discovered in various parts of India. Uranium from this mine at Jadugoda in Bihar will fuel India's first atomic power station, which will generate 300,000 kilowatts of electricity. Besides, there are the black sands on the coast of Madras and Kerala. These sands have been formed by the disintegration of Precambrian rocks in the Nilgiri Hills and the Eastern Ghats. Rainwater has carried this material to the sea, where it has settled down on the beach. These sands contain monazite, a phosphate mineral containing 60% rare earths. Monazite also contains about 9% thorium and 0.3% uranium. Both uranium and thorium can provide fuel for atomic reactors. In her monazite sands, India has by far the largest deposits of thorium in the world. The monazite reserves of Kerala alone are estimated at over 2 million tons. So, India looks to using thorium to fuel her second and third series of atomic power stations. But the sand to the fuel element is a long story. A vibrating screen separates the sand from shells and pebbles and other foreign materials. The sand passes through cross-belt magnetic separators which separate the more magnetic ilmenite, which is black in color, from brown monazite and other minerals. The monazite-rich fraction is further upgraded on a pneumatic table. Here, by winnowing, a product containing more than 97% monazite is obtained. Then, on to the Indian rare earths plant at Arway in Kerala. This plant, started in 1951, treats monazite and produces mainly mixed rare earth salts and a thorium uranium concentrate. The monazite is first dry ground to -300 mesh in a ball mill in closed circuit with an air classifier. The finely ground material is treated with 70% caustic soda at a temperature of 150 degrees centigrade. This converts the phosphates into hydroxides. The trisodium phosphate formed in the process is leached out with water from the insoluble hydroxides. The hydroxides are then filtered on Moore vacuum filters. Most of the rare earths present in the hydroxide cake are dissolved out by treatment with concentrated hydrochloric acid, thus leaving behind the concentrate of thorium and uranium. This concentrate is now dried in a rotary dryer. From the leach liquor, trisodium phosphate is crystallized out. This is a useful byproduct, extensively used for water softening and as a detergent. The plant supplies 1/3 of the world's requirements of rare earths for use in a variety of industries ranging from steel to glass. This earns for the country valuable foreign exchange. The cake containing thorium and uranium is sent to the thorium plant at Trombay. The scene now shifts to the atomic energy establishment at Trombay, not far from the city of Bombay. Here, besides atomic reactors and research laboratories, are the fuel fabrication plant, the uranium plant, and the thorium plant. The thorium plant, the only one of its kind in Asia, was completed in 1955. It was erected entirely by Indian engineers. The process in this plant forms the second stage in the treatment of monazite sand. Here, thorium-uranium concentrate is dissolved in hydrochloric acid and filtered to remove the insoluble impurities. Thorium is precipitated as a sulfate, leaving uranium in the mother liquor, which is separated by centrifuge. Thorium is further purified by reprecipitation as a sulfate. It is then converted into hydrocarbonate of thorium by treatment with liquor ammonia and ammonium bicarbonate. Thorium nitrate is obtained by dissolving the hydrocarbonate in extremely pure nitric acid. Thorium nitrate solution is evaporated and allowed to crystallize in aluminium trays. Thorium nitrate is the main product of the plant, but nuclear pure thorium oxide is also produced here in small quantities. The oxide is sent on to the fuel fabrication plant. Thorium nitrate produced here meets the entire requirements of the Indian gas mantle industry. It is also exported. Now to go back to uranium. This is recovered from the mother liquor of thorium sulfate as a crude uranium fluoride after separation of thorium and rare earths. It is then sent on to the uranium plant. Designed and built entirely by Indian scientists and engineers, the uranium plant was completed in 1958. The uranium fluoride obtained from the thorium plant is first treated with sodium carbonate and hydrogen peroxide. The resulting slurry is filtered, and the filtrate containing most of the uranium is treated with caustic soda. The uranium gets precipitated as sodium diuranate. It is then dissolved in nitric acid to obtain crude uranyl nitrate. This is purified by solvent extraction. The solvent used is tributyl phosphate and kerosene. The resulting nuclear pure uranyl nitrate is then treated with ammonia to obtain ammonium diuranate. This is calcined at 450 degrees centigrade to give uranium trioxide. The trioxide is reduced to dioxide by treatment with hydrogen at about 600 degrees centigrade. Treatment with gaseous anhydrous hydrofluoric acid converts the dioxide into uranium tetrafluoride, which is the most suitable material for reduction to metal. In all operations involving the handling of radioactive material, every care is taken to protect the workers from radiation. Health physicists keep a constant check. Film badges worn by the workers indicate the amount of radiation they are exposed to. Wearing of masks is a must where there are hazards from dust and fumes. The reduction vessel where the fluoride is reduced to metal is lined with dry calcium fluoride to prevent the hot molten metal coming in direct contact with the vessel. Uranium tetrafluoride is mixed with calcium metal granules and the mixture is poured into the vessel. A magnesium ribbon is very carefully attached to the contactors provided to ignite the mixture. The lid is then fixed and the vessel is moved to an isolated room. The vessel is first evacuated by a vacuum pump and then filled with argon gas. A remote switch is then used to ignite the magnesium ribbon, which in turn initiates the reaction between uranium tetrafluoride and calcium. The reaction is instantaneous and violent. The vessel is cooled for 24 hours before the metal is finally obtained in the form of an ingot. The purity of uranium is of utmost importance, for even 1 part of impurities like boron and cadmium in 1,000,000 parts of uranium makes it unsuitable for use in reactors as fuel. Uranium cannot be charged into a reactor in odd-shaped chunks, the way coal is shoveled into a boiler. It is essential that the fuel is charged in the form of regular-shaped elements such as rods, plates and tubes. For the CIR and Zerlina reactors, uranium ingot has to be fabricated into rods before it can be loaded into a reactor. This is done at the fuel fabrication plant. This plant too has been designed and set up entirely by Indian metallurgists and engineers. Fabrication and assembly of fuel elements is a highly specialized technology. India is one of some half a dozen countries in the world which fabricate their own fuel elements for atomic reactors. The uranium ingots are charged into a graphite crucible inside an induction-heated vacuum furnace. Due to high reactivity, uranium has to be melted and cast into billets under high vacuum. By this operation, all the gases and volatiles are removed and the slag separated. To ensure quality, cast billets are tested by ultrasonic tester for soundness. The cast billets are heated to high alpha range of 600 degrees centigrade in a horizontal salt bath furnace and rolled into long bars. The rolled bars generally do not possess suitable metallurgical structure for dimensional stability under irradiation. To impart stability, a special beta heat treatment is given to the bar. It is heated to about 700 degrees centigrade and quenched in water. Thus, a fine-grained and randomly oriented structure is obtained. Rods not so heat-treated show in general a coarse grain size and pronounced preferred orientation. For determining the radiation stability of uranium, specimens are preheated to 350 degrees centigrade, the temperature raised to 550 degrees centigrade, and the specimen then quenched at -10 degrees centigrade. This so-called thermal cycling, which simulates reactor conditions, is repeated 1,000 times. Samples having unsuitable structure show abnormal dimensional changes. The heat-treated bar is straightened and machined to dimensions. 1 ton of the fuel elements fabricated here produces 1,800 megawatt days of heat, which are equivalent to heat obtained from burning 6,000 tons of high-grade coal. Thus, there will be a huge saving in the cost of coal transport alone if thermal power stations were based on uranium in areas away from coal fields. The rod is then degreased in trichloroethylene and dried. An aluminium sheath is slipped onto the rod. The assembly is drawn through a special die on a draw bench to ensure firm contact between the aluminium sheath and the uranium rod. The ends are then hermetically sealed by argon arc welding. The uranium is thus completely clad in the aluminium tube. A glycol test is then conducted to detect any pinholes or cracks in the sheath and porosity in the welds. In this test, the fuel element is immersed in glycol and then vacuum applied. Bubbles in the glycol indicate a fault, so this rod has to be resheathed. These rods are faultless and ready for use in reactor. Nearly 300 uranium rods fabricated here have been used to fuel CIR, Canada-India reactor, and Zalina, the newest of our Indian reactors. Each fuel assembly, as loaded into CIR, is about 32 feet, the central uranium section alone being over 10 feet long, perhaps the longest in the world. Now let us take a look at thorium oxide. Thorium oxide is sieved and then mixed with a suitable binder and lubricant in a glove box. The mixture is then compacted into pellets of specific size on a 200-ton hydraulic press. The pellets are then de-waxed at 500 degrees centigrade and sintered at 1200 degrees centigrade in hydrogen. They are then inserted into finned aluminium tubes. The ends are sealed by welding. Thorium can be converted in a reactor into the fissile material, Uranium-233. India plans to make use of her thorium reserves in the later stages of her nuclear power program. The ability to fabricate fuel elements makes India self-dependent in this vital field. This has an important bearing on the atomic energy program of the country. India is self-sufficient in the basic materials required for her atomic energy program. She also has the technical know-how. Her scientists have mastered the highly complex technology of uranium metal production and fuel element fabrication. We have made rapid advances in this field, and we look to the future with hope and confidence, dedicated as we are to developing atomic energy exclusively for peaceful purposes, for the benefit of mankind. It is indeed a triumph of human genius, of mind over matter, that we have today atomic fuel, source of immense power, power that can change the face of the earth, reclaimed from tiny grains of sand.